Okay, let's picture the periodic table for a second. You know that big block of elements smack dab in the middle? Yep, those are the transition metals. And let me tell you, they are absolutely packed with some, well, let's call them chemical superpowers.
I mean, think about it. They're the reason gemstones have those brilliant colors, they're behind the magnetism that holds notes to your fridge, and they're the secret sauce in speeding up chemical reactions that literally make our world run. So what's the deal? What's their secret? Well, that's exactly what we're going to dive into.
All right, so the first clue in this whole mystery, it comes down to their unique electron personality. It's all about how they manage their electrons, and, it's a bit different from everyone else on the table.
So here's the key concept: variable oxidation states. Sounds complicated, but it's not. All it means is that they can lose different numbers of electrons depending on what they're reacting with. I love this analogy. Think of most elements as having just one wallet, their outermost electrons, that they can easily spend from. But transition metals? They've got two wallets that are both super easy to get into, their outer s electrons and their inner d electrons. And that flexibility, right there, is the key to pretty much everything.
And this table just makes it crystal clear. Take a look at scandium. It's pretty rigid. It only ever plays with one oxidation state. But then you've got manganese. Wow, it's a total chemical chameleon, showing off a whopping 6 different states. That is the exact flexibility we were just talking about. That's where all the magic comes from.
Okay, so let's follow the breadcrumbs to our next clue, which is their incredible, vibrant world of color. And this isn't just some random, pretty feature. Nope. It is directly tied to that unique electron personality we just unpacked.
So how does this actually happen? Well, when white light, which has all the colors of the rainbow in it, hits one of these metal ions, the ion literally absorbs just one specific color of that light. That little burst of energy is the perfect amount to make one of its d electrons get excited and jump up to a higher energy level. So what do our eyes see? We see all the other colors that didn't get absorbed, all mixed together. That's the complementary color. It's almost like the metal eats one color from the rainbow and spits out the rest for us to see. And here's a perfect example of that rule in action. On one side, you have the copper-2 ion. Its d subshell isn't totally full, right? So there's space for an electron to make that jump. It loves to absorb orange light, and what's left over for us to see? Blue. But then, look at the zinc ion. Its d subshell is completely packed, 10 out of 10 electrons. There is literally no room for an electron to jump anywhere. So, no light gets absorbed. It all passes right through, and the ion just looks colorless. It's that simple. No empty seats, no color show.
Okay, so we've got flexibility and we've got color. What's next? Well, our investigation leads us to 2 more amazing abilities: a magnetic personality and this power to build huge, complicated structures. And these aren't just for show. They're the building blocks for industry and for life itself.
So why are they so good at building these things? It really boils down to 3 key reasons. First, they're relatively small, and they have a strong positive charge, which basically makes them irresistible to other molecules. Second, they've got those special d orbitals we keep coming back to, and a lot of them are sitting there empty. And third, these empty orbitals are like perfect little docking stations, just waiting to accept pairs of electrons from other molecules or ligands. It's like they're master architects at the molecular level.
And believe me, this isn't just some abstract chemistry concept. This right here, this is the real-world payoff. Hemoglobin. You know, the molecule that's carrying oxygen through your blood right now as you're listening to this? It's a gigantic complex structure, all built around a single atom of iron. It's incredible. Without this special power of transition metals, life as we know it just wouldn't be possible.
All right, now let's talk about that magnetic personality. It's actually super straightforward. It all comes down to one thing. Are their electrons paired up or not? If an ion has any unpaired electrons, each one of those electrons acts like a teeny tiny little magnet. So when you bring a real magnet nearby, they all snap to attention and line up, and the whole material gets attracted. That's called paramagnetism. But if all the electrons are neatly paired off, their magnetic effects cancel each other out. And in that case, the material is actually weakly repelled. We call that diamagnetism.
And this isn't just a vague idea. We can actually put a number on this magnetic strength. Remember that manganese 2 ion from before? Well, it has 5 unpaired electrons, which makes it really, really paramagnetic. There's even a formula for it. But the main takeaway is simple. The more unpaired electrons you've got, the stronger the magnetic pull. That's all you need to remember.
Okay, we are on to our final clue. And honestly, this might be the most important one for our modern world, the catalyst connection.
You see, these metals are absolute masters at speeding up chemical reactions, all without getting used up in the process. They're like the ultimate chemical matchmakers.
So how do they pull this off? Well, it all circles back to the same two superpowers we've been talking about. First, they use those available d orbitals as a landing pad, an active site for other molecules to come and hang out. And second, that amazing ability to just flip between different oxidation states means they can shuffle electrons back and forth with ease, making reactions happen that would otherwise take forever. A great example is vanadium pentoxide. It's a total workhorse in making sulfuric acid, which is one of the most important industrial chemicals on the entire planet.
All right, the case is laid out. We've seen all the evidence, their variable reactivity, those amazing colors, their knack for building complex structures, their magnetism, and their catalytic power. So it is time for the grand reveal. What is the one thing, the one secret that connects all of these incredible superpowers?
It all comes down to one simple, elegant feature: the partially filled d orbital. That's it. That is the secret. Having that just right number of d electrons, not totally empty but not completely filled either, that's what gives them everything. It gives them the flexibility, the space for electrons to jump and create color, the unpaired spins for magnetism, and those docking stations for building complexes and speeding up reactions. It's the one thing that explains it all.
So there you have it. We've unlocked the secret behind the special powers of transition metals. But it leaves us with a really exciting question, one that looks to the future. Now that we know these elements have such a unique and powerful chemical toolkit, what's next? What new challenges in creating clean energy, designing new medicines, or engineering revolutionary materials, what do you think these elements could help us solve?